All right, everyone. So welcome to our first public lecture of 2024. So my name is Hannah Cronenberg. I'm a PhD student here at the Cottrell Space Institute, and I am your MC for the evening. Tonight, we will be learning all about the science behind the cosmic mystery of fast radio bursts from the man who led the team that discovered them. But before we start, just a few reminders. So the Cottrell Space Institute is committed to providing science education to everyone in our community in a positive environment. And to that end, we'd just like to bring everyone's attention to our code of conduct. If anyone has any questions or concerns or needs help, scientific or otherwise, throughout the evening, you can email us at this email address. And there are a few volunteers who you might have met who may be also able to assist you. So for those of you joining online, hello. If you have questions throughout the evening, you can write them in the chat. So before I introduce, or the speaker begins the talk, I'd like to welcome Professor of Physics and TSI Director, Vicki Caspi.
Well, just wonderful to see so many of you here tonight, and I couldn't be more thrilled to get to introduce our amazing speaker, Professor Duncan Lorimer, a longtime friend and colleague. Dunk got his bachelor's in astrophysics from the University of Wales in Cardiff. I really only know this morning, but I didn't know that. But he got his PhD at the University of Manchester, working with Professor Andrew Lyne, who is also a mentor of mine. And but he did a lot of his PhD thesis in Australia at the Parkes Telescope, which is famous for having been the first receiving telescope of the Apollo astronauts. And you can see more about the Parkes Telescope in the movie The Dish, with starring Sam Neill, as I recall. And that's where I got to know Dunk. We observed the sky, searching for radio pulsars for weeks and weeks. It was a really wonderful time. Dunk has, after getting his PhD, he's held research positions at many institutions back at University of Manchester, at the Max-Planck-Institute for Radio Astronomy in Bonn, Germany, as well as at Cornell University in Ithaca, New York, before going to West Virginia University, where he's a professor of physics and astrophysics, and until very recently, associate dean of research development. I would love to tell you some, funny, embarrassing story about Dunk, but Dunk is one of the kindest, sweetest, most dignified people. I don't have any embarrassing stories. I didn't think of any facts. I will share with you that he is an absolute virtuoso guitarist. And I had the tremendous pleasure of hearing him play in person recently. We were at an event together in Hong Kong, and it was an absolute joy. He's won multiple prizes. He's been a Cottrell Scholar. He's a fellow of the American Physical Society, and in 2023, he was the co-recipient with Professor Maura McLaughlin and Professor Matthew Bales of the Shaw Prize in Astronomy, prestigious prize from Hong Kong, actually. And we're so thrilled to have him here tonight to tell us about fast radio bursts.
Thank you. Thank you so much. I really appreciate that wonderful introduction. Let me just share the screen. And So I'm rather softly spoken, so if you can't hear me at the back, do speak up. It's a pleasure to be back in Montreal. It's about my 4th or 5th visit here, and I always come at different times of year, and I always enjoy myself and having a great week visiting the Institute. I'm giving this talk on behalf of my fellow prize winners, Maura, McLaughlin, and Matthew Bales, and going to tell you tonight about the story behind the discovery of fast radio bursts and a few anecdotes along the way. So we're going to be talking tonight about space, and as astronomers we observe the universe with a multitude of telescopes that span different realms of the bandwidth that the universe is presenting to us, if you will. So in particular, we observe all parts of the electromagnetic spectrum. And so our visible light that we see is just a tiny part of that in the center here, and going out to the highest energy photons of the gamma rays. We need telescopes, X-ray and gamma ray telescopes out in space, and down to the lowest energies in the radio, where myself and many folks in this room spend a lot of our time observing. We use large radio telescopes. Each of these instruments provides a complementary view of the universe, and we observe many different sources. And so we're just going to focus on the radio tonight. So here's a picture of what the radio sky would look like if your eyes, instead of receiving regular light, could receive photons with a 5 centimeter wavelength. And so this is the sky imaged at 5 centimeters in the mountains of West Virginia, where I'm currently based at the Green Bank Observatory. And everything you're looking at here, pretty much, those little points of light, those are galaxies, not stars. They're very distant sources. Stars are rather difficult to see with the radio telescopes unless they're incredibly nearby, like our sun. Most of the stars in the Milky Way don't emit much in the way of radio light. So what you're looking at mostly here are distant galaxies into the distant universe. Some of those extended objects you see are supernova remnants, the shells of exploded material from stars that we'll be studying a little bit tonight. So we're going to be talking about fast radio bursts. So let me play you the sounds of them to give you a. So what you're listening to is the background noise of the telescope. Fast radio bursts are those little chirps. So what we've done here is a simulation. We've converted the radio signals into tones. So the highest frequency tone represents the highest frequency of the radio band. So imagine you're tuning your car radio and you go up in frequency. That higher pitch, that's the higher corresponding to the higher radio frequency. So you heard there that the higher frequencies arrive first and the lower frequencies come later. So you get that chirp. And what we found here is a population of objects that was kind of speeded up a little bit there, really, but they're going off, every 30 seconds or so, there's potentially a detectable one somewhere on the sky. So there's this incredible population of sources that were hitherto unknown. And we only found them through studying the sky in a relatively new way using radio telescopes. So to get into that, I want to, just to backtrack a little bit, I want to get you all up to speed on radio astronomy. So Vicky mentioned in her introduction about this beautiful instrument, the Parkes Radio Telescope, where she and I and many others have spent a lot of time. It was built in the early 60s, and it's a 64-meter diameter dish. And as observers, you sit in this in the tower here underneath this gigantic structure as it whirls around, and it's just, I don't know, it's about the most sort of natural way of observing radio waves. You feel at one with the telescope. That makes some sense. And They leave you alone. Once you get trained, you get to stay at the observatory by yourself over the weekend, and there's nothing but you and a telephone to the nearest staff member in case something goes wrong. And sometimes the power fails and you have to manually stow the dish, and it gets really scary because these very large instruments are moving at very high speeds. And so it's just a wonderful place. And we're so privileged to have the land to do this work, and it's still operating today, and it plays a big role in the discovery. So the discovery of fast radio bursts really starts back in the late 60s with the discovery of pulsars. And here's a different kind of radio telescope. This is actually an AI enhanced image from the 1960s. Showing the array at Cambridge. So you can see basically a bunch of wooden posts in the ground with wires stretched between them. And this forms a low frequency radio telescope. So it's monitoring the sky not at 5 centimeters, but at many meters in the FM band. And famously used by Jocelyn Bell and Tony Hewish to study the twinkling of radio sources, and they were looking for quasars, extragalactic radio sources. But as part of that work, serendipitously, they found a new type of radio source known as a pulsar. And here's a picture of Jocelyn. She recently came to visit us as part of a conference for undergraduate women in physics, and still talks passionately about these days when she was doing her work and analyzing what we're seeing a little snippet of here, miles and miles of output, literally paper output from the radio telescope, looking for radio signals. And she found these unusual signals that repeat. You can see up here these little downward pointing blips. Repeats around about every second from a radio source that turned out to be coming from the cosmos. It was at the same position on the sky each day. And this was unlike anything that anyone had seen before. And it started really the era of what we now call transient radio astronomy, which is part of transient astrophysics. So when we talk about things like that, we're really talking about the universe changing on timescales of seconds or minutes, whereas traditionally we think about the universe just being ephemeral and remaining unchanged. So we're talking here about very transient and dynamic phenomenon. So it was fairly quickly realized that these pulsars that were discovered at Cambridge were really rotating neutron stars that are formed in the supernova explosions of massive stars. So about once a century in our galaxy, the Milky Way, a star will explode, it will use up all of its fuel and succumb to gravity in this violent supernova explosion, where the core of the star gets compressed to about 10 kilometers, and the outer layers of the star bounce off this compact core and stream out into space. So what you're looking at here are the remains of a supernova explosion that was observed by our ancestors in the 1054 AD. It was seen as a bright object during the daylight hours for several weeks. And now when you point a telescope at it, an optical image, you see something like this, an expanding shell of gas. And what we've done in this little image here, or what one of our colleagues did, was to superpose that trace coming out of it. It's a suggestive image that shows the radio emission coming from the center of that supernova remnant. So what you have is a rotating neutron star, and my arms here are the north and south magnetic poles of the star. And as getting rather dizzy, as the poles sweep past your line of sight, you get one of these pulses that's emitted. And it was soon realized that from this particular source was rather unusual, and that it emitted about 33 pulses a second. something like about 30 pulses a second. It's spinning at 30 hertz. But every couple of minutes or so, it emitted a really giant pulse, something that was much, much stronger than the average emission. And these are these spikes that you're seeing here. They're so bright that you could see it well beyond the extent of the Milky Way galaxy. This particular source, the crab, is well within our galaxy, the Milky Way. But you could see these sources much, much farther out. And so that really set people on a journey of discovery. And one of the things that Vicky and I and some of the colleagues in the room have been working on is looking for pulsars over the years. And that's when I first met Vicky, that's what we were doing. We were searching for pulsars with Parkes and other telescopes. And this dispersion technique that you heard in the audio it's been well known to us for many years. And what we typically do with pulsars is we point a telescope at a part of the sky, and we carry out a search for pulsars by just collecting data for several minutes and averaging the signal during that time. We don't really care about these brighter events. Most pulsars don't actually emit these really bright pulses. They're mostly very faint. So we have to average the signal over time. When we do that, we see that the emission has this chirped behavior where the high frequency signals, the yellow band there appears first at earlier times, and the lower frequency signals arrive last. What's happened here is that the pulse, as it travels from the pulsar to us, it's interacting with free electrons in the space between us and the source, and it's slowing down the lower frequency pulses at a higher rate than the higher frequency ones. So you get this chirp. It turns out to be a really useful tool to study pulsars and also fast radio bursts. So, we could have a whole lecture on pulsars, and I'm sure there have been some in this series. But what was happening in the meantime, as people were finding pulsars, people kept thinking about these giant pulses and how could we find these sources in external galaxies? By the year 2000 or so, we've known of about 1,000 pulsars within the Milky Way, but we still haven't found anything beyond the Milky Way. And so a number of people were really interested in trying to search for these bright objects. And the group here at Cornell University, Jim Cordes, Shami Chatterjee, and Maura McLaughlin, who's one of my fellow Shaw Prize winners and my wife. This was before we met. She hasn't really changed. Obviously, she looks just the same. But she and her colleagues at Cornell University were really intrigued by this idea, and they started developing techniques to search for these mysterious events. And it turns out to be a relatively straightforward process. It's just that people were so enthused about finding pulsars that they kind of lost the thread for a bit, and they had to go back to basics and start looking for these giant pulses again. So to cut a long story short, what Maura, Jim, and others did was that they came up with this pipeline, is what we call, to analyze our data from these radio telescopes. And they generated plots like this through a computer analysis. And so they were visualizing the data in time, running along this axis. And then this delay that we saw the pulsars exhibiting, which we can characterize by something called the dispersion measure. You can really think of this as distance going up the vertical axis here. So it's kind of distance versus time, if you will. And those big blobs there, those are bright individual pulses that the algorithm has detected, and amidst the background of noise, which are the smaller symbols. And so armed with this new way of looking at the data, which is really just a computerized way of how pulsars were originally discovered, but doing it in a very, very efficient manner in the computer, they were able to now start looking for sources in data sets. And so the story of the fast radio burst discovery really, took many years to develop in that sense. And then when Maura and I later came to West Virginia University, which is now about 18 years ago, here we are in our first summer at WVU. I was trying to grow a beard at the time, and there's Maura holding our now 18-year-old son. We just arrived, and there's the Green Bank telescope in the background there. We were looking for ways to engage students quickly, because we wanted to get, show our new employers that we were worth their investment. And so we had lots of students coming to us. Here's one of our first students, Ash Markovic, who was looking for a project, and we thought, well, we could just use this new technique that Maura had developed to start searching for data sets. And the nice thing about it was that you could give it to a student, they could analyze it on a desktop computer, and it was something that you could do in a relatively short space of time. It would take a few months to analyze the data over the course of a semester. So it was almost the perfect project for a student to get involved in. And we decided to look at these little neighboring galaxies here, the large and small Magellanic Clouds, which you can see from the southern hemisphere. I don't know how many people have seen these Magellanic Clouds. Raise your hand if you've seen them. So a few of you. They are definitely things to make well worth making a trip down to the southern hemisphere to look at, because they really do just look like clouds. They're so bright if you go to a dark spot. And anyway, they turn out to be one of our nearest neighboring galaxies, and so a great place to start looking for these extragalactic pulses. So we got hold of some data, and we graciously were able to get that rather quickly from a paper that Vicky and one of her former students, Freddie Crawford, and one of our advisors, Nick Manchester, had published. Actually, it was in that year, 2006, where they had found some pulsars in the Magellanic Clouds. And we thought it would be fun to look for individual pulses in the data. And the signal that we found was seen using a multi-pixel camera. So your phone has thousands of pixels, I guess millions of pixels. This is a multi-pixel camera for a radio telescope. There's 13 pixels on this camera, but for radio astronomers like me, that's an amazing advancement, because it allows the telescope to look at 13 positions at once. You can cover the sky very efficiently. We ended up finding this source that I'm about to show you down here, a few degrees south of the Magellanic Cloud, really by chance that we had this extra piece of data that was covered by this survey. So there was a lot of good fortune that came our way, and I'll show you how that looked. So what we were really looking for, we were taking this code, and we were looking for little blobs in the time dispersion measure space that corresponded to individual pulses. This is actually a detection of individual pulses from a pulsar in the Magellanic Cloud, but it was already known. Vicky and others had already found it. So it was verifying that our technique was working, but there was nothing new there. And so this went on for quite a while. So Ash would bring me some plots every week, and we would look at them together. And then he showed me this one time, and it was quite extraordinary. You can see this really bright event that's just, it's actually so strong that it saturates the observing system. And it was seen in multiple pixels of the camera, way down south here, a couple of degrees away from the Magellanic Cloud. So it was unexpectedly bright. It had an unexpectedly large dispersion measure, and it was an unexpected position. So it really was it stuck out like a sore thumb. And we got so excited by this that we went back to the telescope and observed for many, many hours, looking at that same spot in the sky to see if we could find some repeat pulses, because that's kind of what we've been trained to do. Whenever we find a pulsar, we go back to the same spot to see if it's there. We found nothing in 90 hours, but we were so convinced by the pulse because it really showed all the hallmarks of an astrophysical object. Here it is shown, this is the pulse now in time versus frequency space. So what you're looking at there is only half a second of data. And the pulse, you can see, is that high frequency to low frequency sweep along here. This horizontal line here, that's just a malfunctioning frequency channel. And then when you add up the data along that pulse line, then you get the inset. That's the pulse itself. And so it was just a remarkable event. We did all of these various checks on our data. We looked at it many different ways, and we eventually wrote up our findings, where we had this putative object, this object that was really the forerunner of a putative population of sources that were brand new, extragalactic sources that we've never seen before. What was remarkable about them, and I'll show you an estimate of the distance in a moment, but they were 1 trillion times brighter than what we would expect for one of those cloud pulses. It's about the equivalent of what the sun puts out in a month. These sources are putting out in a few milliseconds. What's more, when we extrapolate it, and as scientists and astronomers, we like to make inferences from our conclusions. When we took account of the fact that the telescope was only seeing a small part of the sky, we extrapolated and said that hundreds of these events would be going off every day. And so what we were basically saying was that there's a new class of sources that are out there in the cosmos, of which we've only found one. So we were really sort of pushing in all our chips onto the table. But we had good reason to do so. And this is the picture that we had in our mind's eye. It's been sort of glorified. This is now, but this is basically what we were thinking back then, that we were sitting in the Milky Way here, and rather than seeing something just outside the Milky Way, we'd actually seen something that was coming from way into the distant universe. And when we estimated the amount of dispersion that we observed, how that could be produced by the electrons across the universe, we came to a staggering conclusion that this source was about 3 billion light years away, and we didn't see it, a galaxy when we looked at that position in the sky. We didn't know the position well enough to do anything like that. But this was kind of the picture that we had, that there was something going on in a distant galaxy. It emitted a pulse and it traveled across to us. So to give you kind of a very quick timeline, the pulse was probably emitted from the source. It looked like this. It was emitted at all frequencies at the same time. 30,000 years later, it leaves its host galaxy. It's dispersed a little bit. Then it travels across the universe for the next couple of billion years and arrives at the Milky Way, and then 30,000 years later, it gets to the Earth. So all of these dispersion measure contributions are folded in to this to the pulse that we see. So it's kind of like a fingerprint of its. It's like a little travel, like having your passport stamped as you go through various countries. And we've got a record of how it's traveled across the universe to us. So in the paper that we put out, we made some bold suggestions as to what it might be, but we really didn't have too much to go on. We knew that it occurred over a short time scale, a few milliseconds. So that means it could only be, a few light milliseconds across. It couldn't be a whole galaxy doing this, because galaxies are thousands of light years across. and it was very energetic. So it was something that's small, it's coherent, it's able to produce the radiation in a short space of time. And as far as we could tell, it only did it once, at least once in 90 hours. So we were thinking of things like maybe collisions of stars or explosions of stars or some type of exotic burst, but we really didn't have a good idea back then. We put out some basic arguments, but it was really our colleagues that came later with theoretical interpretations that have led to the rest of the story that I'll tell you. Let me just make a brief aside for a second. That initial object that I showed you became known as the Lorimer burst. I didn't name that, somebody else came up with it. And it just kind of stuck in the paper and became part of the folklore. But it's entered popular culture now. If you look, there's a book about relationships that you can find. The Lorimer burst is in chapter 5 there. And if a burst can travel billions of light years across the universe, you can work things out with your partner. I'm paraphrasing a bit, but and then there is a German rock instrumental band who go by the name Lorimer Burst, and they have an album out called Dispersion. And my cousin is from Hanover, and she was visiting her family. I told her about this, and she went to go to see them in concert, and she told them who she was, and they were like, "Oh!" They were worried I was going to sue them for copyright. Anyway, it's actually pretty good music, and I've had a few back and forth with them by email. Anyway, it's, for better or for worse, it's part of the culture, but there's a lot more to the story than that. So let me try to get back to the rest of the story. So this all happened in 2006, 2007. Of course, the next step is to see if you can find more of these objects. And so, everybody who had access to a radio telescope, naturally was very curious and wanted to search for them themselves, which is exactly what we wanted to happen. What we didn't expect to happen was that things like this would start to be seen in the data. We get these sort of strange dispersed pulses that were much sort of blobbier in nature, but they were occurring in all 13 pixels of the camera. So they were coming into the telescope actually, and probably not from hitting the surface of the dish. They were coming in from a different direction. So they were really they were not really, they were similar but different, if that makes sense, to the original Lorimer burst. So they were, but they were published, in the scientific literature and dubbed peritons after this mythical Greek elk that casts a human shadow. So it's basically something that's masquerading as something else. And our colleague now, who's a faculty member with us at West Virginia University, was the founder of the finder of this this group of sources, and they made the plot thicken for a while, because it really wasn't clear at that point. Well, you had this original source, you had one of them, and then you had all these peritons. What's going on? It's clear that the peritons didn't look like an astrophysical source, but does that mean the other one is discounted as well? And so this went on for like 6 years. You can imagine this is quite a, I'm speeding up the story a bit here, but you can imagine the thought processes that are going on in our heads over this time. Did we make a mistake? What was happening? In the meantime, we were all looking for more signals. One of the breakthroughs really was made by this group here, also a survey at Parkes, where they found 4 more examples of these bursts at different dispersion measures. Here's our original one, and then here's another one that was found around the same time. What you're looking at in that plot is dispersion measure versus galactic latitude. So if you recall from your astronomy classes, that's the angle from the galactic plane. I introduced that just to say that this is the behavior that you expect for galactic pulsars. These are pulsars in our galaxy. And then these things out here, these are the anomalous objects that were really quite different and they're much more distant from and distinct from the galactic pulsars. So this group coined the name fast radio bursts. They were no longer called Lorimer bursts, which was a good thing, really. And fast radio bursts is more descriptive, fast because they occur in short duration radio. They're in the radio band when they burst. But it was also to kind of give a nod to gamma ray bursts, which are energetic explosions in the gamma ray band, which may or may not have anything to do with fast radio bursts. So we went from one object to having 6, so that's suddenly a population. But then you're wondering, well, what happened to the peritons? Well, Emily Petrov, who was formerly a student down at Swinburne in Australia, and also recently here at the TSI, was really cracked the code and realized that there were actually signals that were generated very locally, actually in the observatory canteen where they had microwave ovens. By that time, 2015, the technology had advanced to such an extent that you could actually detect these bursts in real time. So the computing no longer took months; you could do it within a few seconds. And so here's a scientific experiment they had where John, one of our colleagues at the observatory, he got a pool cue for some reason, for dramatic effects. He's about to open the microwave door when it's still running, like you do when you get impatient and you want your food before the cycle is finished. When he does that, there's a magnet spinning, it emits an electromagnetic pulse, and that's what's seen by the telescope. And then they were able to connect those two together. They also wrote this up in the paper, and they had this nice graph that shows the distribution of peritons versus time, and they show that they peak around lunchtime. You want to check that out in the paper. So it kind of brought that to rest, and you might be wondering when the Lorimer burst was what time that was seen. It was 5 a.m. So we're safe on that one too. But thanks to Emily, we were able to sort of move on from that. And really, the community by that time was saying, yes, we're really committed to this. Let's go and invest even more resources in them. And so a few highlights over my next few slides now. In 2016, things have happened very quickly. The first repeating source was found. Vicky and others in this room have been involved in that discovery. And it was really a breakthrough moment because this was almost 10 years after our initial discovery. Up until that point, we'd never seen one go off more than once. This one was suddenly starting to have these outbursts where you could see multiple pulses. And it was clear that it was a repetitive, recurring phenomenon. So for this particular source, it wasn't something like a gigantic explosion. It was something that was perhaps building up over time and then releasing energy before starting again. This was discovered using the Arecibo telescope in Puerto Rico, which is sadly no longer with us. The discovery itself was also important because it meant that you could actually, with confidence, point other instruments at that position. And, it wasn't a complete waste of time to wait for the source to go off. We knew that one was going to go off sooner or later. And that's exactly what the group did. This was led by Shami Chatterjee, and they had the very large array looking at this source on multiple epochs. And finally, it went off. The source was detected. And the very large array, it basically synthesizes a telescope with really fine angular resolution. It's able to resolve radio sources on the sky to much better precision than they can be with a large dish, paradoxically. And so it was able to locate, if you look in the frame here, they were actually able to say very robustly that the FRB was coming from this position on the sky, and there's a galaxy right at that spot whose redshift and distance they could measure. And that was the first time that a direct distance measurement was available to a fast radio burst. And this particular one was about 2.3 billion light years away. This was the first time that we were really confident that they were beyond the Milky Way. There was really no doubt at that point that this is a cosmological population. And so then enter the stage of CHIME, the Canadian Hydrogen Intensity Mapping Experiment, which is well known to many of you in the audience, and it's one of the premier radio instruments in Canada, and it's been used in many different ways. It's this group of cylinders out in British Columbia that is basically just scanning the sky as the Earth rotates, used for many different experiments, and Vicky and others realized that it would be an excellent way of finding fast radio bursts, because it looks at the sky every day, and crucially, it has a very large field of view. So it's able to find once they got it wired up, they started finding about 3 fast radio bursts every day. We've been doing so ever since. And this has suddenly exploded the number of sources that are available. We went from having 30 sources to hundreds of sources, thanks to what CHIME has told us. So one of the things we found is that as we've started looking at these fast radio bursts, they occur in all different types of galaxies in many different environments. Sometimes they're out in the spiral arms of galaxies. Sometimes they're at the cores of galaxies. And one particular case, they found a source in a globular cluster, which is a very old population of stars where you wouldn't expect young, highly energetic pulsars that could emit giant pulses to live. So this is adding to the story. The plot thickens even more. 2020 was a disastrous year for many of us, but it was a good year for FRBs because there was a magnetar found in the radio in that year, an individual pulse from a magnetar. So a magnetar, I should say, is a supercharged version of a pulsar. It's an intense magnetic field. And these have been studied at radio and X-ray wavelengths, and they've been shown to be highly energetic neutron stars. But this particular one emitted such a bright pulse that it was seen not only by CHIME, but by this little guy here, STARE-2, which I think is the world's smallest FRB detector. It's basically the size of a large cake pan, and it observes the whole sky. It's really optimized for extremely bright sources, and it has a wide field of view. And so together, these two groups detected this one-off event, incredibly bright event from this magnetar. It looks just like another fast radio burst. So this looks like a really strong case for a fast radio burst object that's going off in our Milky Way. So not only do we see them in just about every other type of galaxies, we think they are going off in the Milky Way too. I should give a nod to Vicky for her work on magnetars, along with Krista Kubilotu. They also won the Shaw Prize a couple of years ago for their contributions to this field, and through their pioneering techniques in X-ray astronomy, they've shown that these magnetars, they form a distinct population of the neutron star zoo, and that's led to a lot of good theoretical input to fast radio bursts. So many of the theories for fast radio bursts are that they're produced by the highly energetic environments that magnetars provide. We might, the jury's still out on those, but they certainly are very, very strong candidates. So I'm coming towards the end of my presentation now, and many fast radio bursts are now localized. About 40 out of the almost 1,000 that are in the public catalogs are actually localized to galaxies where we can really say, yes, it came from that galaxy. And as I mentioned earlier, we see them in all different types of galaxies. Even the so-called red and dead ones where star formations cease, they're slightly less prominent there, but they're pretty much ubiquitous among the galaxy population. So what we really have now at our disposal are really a new probe of the population of objects in the universe. Through FRBs, we can start to carry out radio observations that sample the electron content along gigantic lines of sight across the universe in a way that simply wasn't possible in the past. The most distant fast radio burst that's been confirmed so far is an astonishing 8 billion light years away. For those of you who know about redshifts, that's a redshift of 1. It puts out as much energy as the sun puts out in 16 years. And it's an incredibly luminous object. And it really implies that that similar objects can be detectable out to even greater distances. So the hope now going forwards is that we can use these FRBs really as probes of the electrons in the universe. I kind of liken it to, when you go to measure your oil in the car, you stick the dipstick into that little slot, and you pull it out and you see how much oil there is in the car. You can kind of think of these FRBs as a dipstick into the universe, where you're measuring the number of electrons across the universe. They are just, it's something that we would never have thought possible 20 years ago, to have these things now at our disposal. So we're so lucky to have them. I'm going to just close just talking very briefly about some of the many open questions that myself and colleagues here and around the world are looking into. Some of the things that I didn't really have time to get into in this talk, but one of the big questions is, do all FRBs repeat? We see basically about 10% of the current sample right now. We know that they definitely repeat. The other 90%, well, maybe we haven't observed them long enough to fully establish that. Is there really a single class of fast radio bursts? Are they coming from all the same type of object? So that's not clear either. As I mentioned, FRBs seem to be ubiquitous. They're coming from many different types of galaxies. That would suggest that they're coming from many different types of environments. And that would also suggest to me that different types of sources could be involved. One of the ways that we'll be able to, or we are deciphering this, is by looking at the event rates of repeaters versus one-off sources, and trying to connect those to the event rates of other transient phenomena that we know of in the sky. So things like gamma ray bursts or gravitational wave events, supernovae. Those are things that we're trying to either investigate more or rule out as sources of fast radio bursts. What I didn't really talk about here were the periodicities. We know from pulsars that they spin very regularly. They have a rotation period, and those have been used for decades to really act like clocks in the cosmos and use them as clocks. Fast radio bursts, we think, are produced by some sort of neutron star phenomenon. So it's reasonable to think that they maybe have a periodicity too, but we so far haven't detected anything like the spin period that we see in pulsars. There's a couple of really interesting sources that have brief hints of a periodicity, but so far they seem to be much more sporadic, let's say. Well, one of the things that has been determined by the Chime collaboration and others now is that a couple of FRBs have periodic episodes of activity. That is, that they are active on kind of seasonal time scales. So every 16 days, one source will go off for a few days, and then it will shut down. But within that activity window, the pulses themselves are still pretty much randomly distributed. So there's a lot of differences, but also some similarities to pulsars. As you can imagine, then it's kind of a theorist's paradise. at one point there were more theories about fast radio bursts than there were fast radio bursts known, literally by a large number. Even after the first few, there were already 30 theories out there. We still don't really know what they could be. That and one of the challenges there is that even though they're very energetic objects, and very energetic events, there are many different astrophysical scenarios that we know about that can produce that amount of energy. And so, merging of two white dwarfs, for instance, or supernova explosion, just a tiny fraction of energy from those events can produce a fast radio burst. And so there are a lot of corridors that we need to go down to try to understand those more. I mentioned them being used as probes of the universe. I think that's something that's really is now happening, and I think in the next 10 years will tell us a lot about the content of the structure and the content of our universe. So it's been an amazing story to be a part of. This is really a thank you on behalf of Matthew and Maura and myself. We have our own funding agencies to thank here. Some of these will mean less to people in the audience than they do to me, perhaps. But I want to thank you, the taxpayers, for funding just science in general. Without your tax dollars in every country around the world, literally none of this would be possible. And many of the scientific advances that we've enjoyed would also not be possible. So we, as astronomers, we bring scientists into the field. We attract them through astronomy, but most of our students will find other contributions into the community, but they've been brought into science thanks to the research that you're able to fund. So thank you for that. I also want to thank our collaborators, Brony and Ash, for their contributions to that initial work. It was an amazing time to be doing this discovery. And Maura and I, in particular, have many students that we want to thank over the years that we've had the pleasure of learning from as we've worked with them. And we continue to do that along with our colleagues and postdocs. So thank you all for indulging me tonight, and I really appreciate it.
So we'll open things up for our question period. If anyone has questions, you can just raise your hand, and I'll also just check the chat.
So those pulses at the beginning of the lecture, you said every 30 seconds, they're due to what?
Every 30 seconds, we think a fast radio burst will go off somewhere on the sky. And the challenge is that our telescopes don't monitor the whole sky the whole time.
Would you mind repeating the question before?
Oh, yeah, sorry, yeah. So the question was asking whether the pulses go off every 30 seconds.
No, you were saying there were small pulses due to pulsars rotating, and then there were larger ones.
Oh, the giant pulses from pulsars versus the regular pulses from pulsars. So I think that was the question that you had. So a pulsar spins, right? So let's say I'm a 1 second pulsar. I'm going around about 1 second. You're seeing this emission from me about once a second. Most pulsars are emitting fairly steadily, that each pulse is more or less the same amplitude. And some of them are just very weak, that you have to add up many, many pulses to get a detection. But these giant pulses are unusual in that something in the emission process is organizing the radiation to radiate at a much greater intensity for one single pulse. It sort of releases this energy. And that's what you see is those giant pulses. They're actually quite rare in the pulsar phenomenon. We mostly see just the faint ones.
Even not all pulsars in them?
No, it's just a small, so out of about 3,000 pulsars that are known, only a few dozen are known to emit giant pulses. Most of them are just emit very faint pulses. Yeah.
Why is that?
Well, you tell me. It's after 50 years of studying the emission mechanism, we understand some of the basics that the electrons are accelerated in the large magnetic fields of the neutron stars. But it's for some of these pulsars, they have a very high magnetic field component further up in their atmosphere that causes the particles to accelerate and organize. But there's still a lot of details to be understood about that. Most of them just aren't as efficient as that, and they radiate weakly. Yes.
So I just wanted to ask, can you?
Yes, I
I
can do.
wanted to ask, like, as you say that I guess years of studying it, you're just like trying to get to know the basics. So I was wondering if it's really important for us to know, as in like, does it have any real life uses? Just studying the pulsars, like pulsars in our life.
So you're asking what the real life applications are?
Yes,
Yeah.
is it like important to know it for any kind of application that we could actually use in like in some sort of?
Oh, okay. Yeah. So the question is, what would is there a real world application for studying FRBs beyond just attracting people into science? It's a great question. For pulsars, I'll just pivot a minute. For pulsars, they're in the galaxy. People are actually devoting quite a lot of research into using them as a galactic GPS, a navigation system for spacecraft. So by timing the signals for pulsars, you can triangulate off of the, you can triangulate your position if you're roaming the galaxy. For FRBs, they're more sporadic, so you couldn't really rely on them to do that. I'm trying to think of a good application of them beyond doing really for astronomers in general. They're probably most useful for measuring the large scale structure of the universe and the magnet. You can also use them to investigate the magnetic field of the universe, but that doesn't really pervade into everyday life as much.
So still like has some use. It still has some use.
Oh, it has a lot of uses for astronomers. It's like, this is just suddenly like an additional tool in their toolbox that they can use. So that's the big importance that I think is brought to a larger community than just people who are interested in them for their own sake. Yeah.
Have you been able to categorize what the Milky Way, or like depending on the types of galaxies they come from, or is it still pretty random?
So I missed the middle part of that. Depending on
Have you been able to categorize them in the Milky Way, or is it still pretty random?
right, categorize them in terms of their galaxy association.
Yeah.
So the main subcategorization right now is either repeating sources or not. We see repeating sources in different environments. They're a smaller fraction of the total population, but we see them in different environments already. So there's not a clear association there that I'm aware of. For the one-off sources, they're in different environments too. So in that sense, I think that somebody in the room might want to correct me, but in that sense, that I think we haven't really seen any strong preference yet. Yes.
I'm not accusing anybody of false advertising or anything like that, but I thought I read in the blurb for your talk, you could talk about the architecture of the universe. And you did just mention something just now in response to another question. That just might give us clues about something like that. Could you just give us a hint of what?
Sure. Yes. So the dispersion effect that pulsars and fast radio bursts give us tells us about how many electrons the signal has encountered along its path to us. So pulsar astronomers have used that over the years to map out the electrons in the Milky Way. It's kind of a unique way of doing it. So in addition to the stars in the Milky Way, we have gas. And as part of that gas, there are these free electrons that are moving around the Milky Way. They're a very important component of its structure. So the FRBs really are like the large scale analog of that. It's allowing us to look at the distribution of matter between galaxies. And that's you could think of that as the large scale structure of the universe. So, we're able to measure the distances to galaxies, and we're able to measure that electron component in other ways, but the FRBs give us just a new and actually very precise way of doing it.
The Crab Nebula is pretty well known.
Yeah.
What type of object is that?
So the object at the center of the Crab Nebula is thought to be a neutron star. And so that's that's this collapsed object after a supernova has exploded that is about the radius, 10-kilometer radius, and just over the mass of the sun. So it's incredibly energetic, and it has a large magnetic field, and it's actually powering the emission that we see in the Crab Nebula as well. For a long time, it wasn't known why the crab was still radiating. And the neutron star at the source is kind of lighting it up.
Jeff, another question.
Yeah.
Why can't we see those extended? Why can't we see those extended objects that we see in the radio sky and physics?
Well, we do. In fact, some of those extended objects that I showed you were supernova remnants. So they're radio versions of supernova remnants. So you're seeing the radio emission from electrons spiraling in a magnetic field, but they're tracing the structure of the supernova remnant. So they actually complement each other.
So you can't see.
You can see them, yeah.
There seems to be lots of unknowns in your equations describing the FRBs, because we don't know what a standard power would be. And at the same time, we determine a distance.
Yeah.
The amount of matter they traverse, and then we determine what we